Can everybody see the board okay from where you're sitting? We're all good? Okay. All right. So the first graph that's written on there, the work is already kind of shown for you because you guys have done problems like this before. You did it in maybe Math 1, maybe Math 2, where you would look at a quadratic, and the first thing you would do is, hold on, I feel like that's not all the way focused. Okay, the first thing you would do is you would look for the x-intercepts. So we can go ahead and label this on our papers. We have x equals positive 2, x equals positive 4. And so then you would take those x-intercepts and you would write them in the factored form, which would be x minus 2, x minus 4. And then you would just go ahead and FOIL that. So you would do x times x is x squared. X times negative 4 is negative 4x. Negative 2 times x is negative 2x. And then negative 2 times negative 4, that's a typo, is positive 8. And then from there, you would just combine like terms. And so the negative 4 and the negative 2 gives you negative 6x. And so then you could say, all right, in the standard form, the quadratic is f of x equals x squared minus 6x plus 8. The other form is the form that we worked with before. And some of you guys noticed it on the worksheet and said, oh, that's a weird phrase, but it's called linear factorizations. The linear factorizations, and those were the ones that we kind of liked because you could see what the x-intercepts were and you could see what the multiplicity of the x-intercepts were, so they were kind of nice. So you always write it in the linear factorizations first, and then you only do the standard form if you have to, because the standard form involves foiling, and I don't know about you guys, but I don't like to foil unless I have to. So you're going to read the instructions for problems carefully, because if they don't say to write in the standard form, then you're not going to, because we like to avoid the foiling if we can. Okay. For the next one, it says that we have an x-intercept of negative 1, so I'm going to go ahead and label that on the graph. X equals negative 1. And then we also have an x-intercept of positive 3. But the x-intercept of positive 3 has a multiplicity of 2. Has a multiplicity of 2. So it's x minus 3 in the parentheses. If you were to write it as a factor, it'd be x minus 3. And then the x-intercept of negative 1 would be x plus 1. But since the x-intercept of positive 3 has a multiplicity of 2, when you put it in the parentheses in the factored form, you write x minus 3 squared. There's 2 of them. Question? You just killed a baby wolf. Okay, so we don't say hypercube. That's not a mathematical term. That's a nerd term.
How do you tell the difference?
We're just gonna, in this class, we're only gonna use 1, 2, and 3, because you can't really tell the difference. All right, so here's the linear factorization. And then how could I tell that there should be a negative in front of the problem? Just by looking at it. Anyone know? Yeah, Annalise. Yeah. Yeah, so the arrows, you have one going up and one going down, which means it's got an odd degree overall. And then the first arrow points up, the second one points down, which means that my pencil goes like that, which is overall a negative slant. So I'm going to have a negative coefficient. Okay, so with this one, whenever I need to multiply all this out, FOIL all this out, I got to kind of expand things, right? So I've got an x plus 1 and then an x minus 3 and an x minus 3. And so what I have to decide is how am I going to FOIL this out and make life easy for myself. So what I did is I just chose two parentheses to FOIL. I ended up taking the x minus 3 and the x minus 3, and I chose to FOIL those. It doesn't matter which one you FOIL. You could have done the x plus 1 and the x minus 3 and FOILed those first. It doesn't really matter. I happened to choose the 2 on the end. That was my choice. It doesn't really make a difference though. So then I took this and I did the x times x to get the x squared. And I did x times negative 3 and negative 3 times x. That's how I got the negative 6x. And then I did the negative 3 times negative 3, and that's how I got the positive 9. Does that make sense? Everyone comfortable with that? Okay. And then over here I had the x plus 1. So I still haven't dealt with the fact that it's got a negative sign in the front. I'm not worried about that quite yet. Okay? And then the next thing I did is I said, well, I need to FOIL these. Now, even though I'm a math teacher, I do not like FOILing anything that's bigger than a binomial times a binomial, which is why the next thing you see in the notes is me using the box method to multiply these out. I do not like FOILing anything bigger than that. So since I had two things multiplied by three things, I made a box that was 2 by 3. Everyone see that 2 by 3 box? Okay? So I have x, an x, a positive x, and a positive 1, because I'm not dealing with that negative sign yet. And then I had a positive x squared and negative 6x and a positive 9. We comfortable with everything so far? And then I just multiplied it like a multiplication chart from back in elementary school when you guys were first learning how to multiply numbers. So I said x times x squared is x to the third. 1 times x squared. I have so many typos on here that I did not notice. 1 times x squared is x squared. Let's fix that. X times negative 6x is negative 6x squared. I think I did that to make sure my students were awake. So we're awake now. Good thing. 1 times negative 6x is negative 6x. X times 9 is 9x. And then 1 times 9 is 9. Right? And then from there, you can just combine all your like terms. So x to the third is x to the third. X squared and negative 6x is negative 5x. Negative 6x and 9x is 3x. And then 9 is 9. So I combined my like terms there. Notice I still have the negative in the front. I was still hanging on to it. And then my very last step was to just take that negative and distribute it to my terms. And so this was my final equation. And this is the equation written in standard form. Okay, we are about to do one for ourselves. Are you guys ready to do that? Okay, so what are the x-intercepts for this last example? I got x equals, what's this one? Negative 5, x equals negative 1, x equals, and x equals. Okay, so that means that f of x is going to be x plus 5, x plus 1, x minus 3, x minus 4. Okay, so when we FOIL, we can only FOIL two sets of parentheses at a time. So what I want you guys to do is take a moment, and you're going to FOIL the first two and see what you get. And you're going to FOIL the second two sets of parentheses and see what you get. Okay? FOIL the first two, see what you get. FOIL the second two, see what you get. And then once you are done, you can go ahead and look up here and see if you got the same thing that I got. How are we with our foiling? We got it? Everybody got it? Good? Marvelous. Okay. Now, we are going to have a trinomial times a trinomial, which means 3 things times 3 things, which means I am not foiling, because gross. Barf. Blech. So what I'm going to do is I'm going to draw a box to help me multiply. And how big do you think my box needs to be? 3 by 3, because I got 3 things times 3 things. Now, I just want to make sure that I didn't forget anything. So if you guys look at the graph, does my graph have a positive coefficient or a negative coefficient? Positive, how can you tell? Yeah, both of the arrows go up. So this is a graph with an even degree and a positive coefficient because both arrows go up.
Whether or not negative is equal to whether or not the positive end goes up.
Well, if that goes up and it was even, then that would be a positive coefficient. But if that goes up and it's odd, then it's a negative coefficient. So it makes a difference.
The positive line goes up, then wouldn't it always be?
What do you mean positive line?
So if the right side of the graph goes up, then wouldn't it always be positive, a positive coefficient?
And you could do that if you want.
I'm just saying, like, I don't think it's the left side.
Good. I'm going to check both sides. Okay. All right. X squared times x squared is x to the 4th. X squared times negative 7x is negative 7x to the 3rd. X squared times 12 is 12x squared. So go ahead and keep filling out your box. 12 times 6, anyone? 72. See, why do I have to use my brain for anything when I have you guys? Oh. And then my favorite thing about the box is that the like terms are on the diagonal. Like these are like terms, these are like terms, these are like terms. I don't know, it's kind of nice. All right. I'm going to keep the f of x's coming here because we just always got to make sure that our equation is an equation. It's got to have an equal sign in it, right? To be an equation. That's how they work. So I'm going to combine my like terms at the very end to get my standard form. Anyone want to confirm or deny my final answer? We agree? We disagree? We with it? Yes? What did you have for your plain x's? You had 35, you say?
Oh, I forgot to do. Wait. I don't know what it is.
Typo, maybe? Okay. And then, just for consistency's sake, I'm going to go ahead and label this. So this is the linear factorizations. And then this over here is the standard form. Ta-da. Okay. How are your brains feeling? Feeling pretty good? Okay. We feeling like this is a enjoyable little lesson here? We're like, ooh, yeah, I could sit here and FOIL all day long. More of these, please. No? Well, look, there's more. Eh? Okay. All right. Well, what kind of answers do I get when I solve for x with the quadratic formula? Well, let's remember what the quadratic formula is. X equals negative b plus or minus square root b squared minus 4ac divided by 2a. Okay. So when we have the answers on the first page, all of these types of x-intercepts that we would get from factoring, right? That's why we had the factored form and we were FOILing it out. The question is, what happens if you have the types of x-intercepts that don't come from factoring? What if you have the types of x-intercepts that are like crazy decimals? You know what I'm saying? And those types of x-intercepts, they don't come from factoring, they come from the quadratic formula, right? Right? That's where the crazy decimals come from. So when they come from the quadratic formula, they always come in pairs because they come from having a plus or minus in front of a square root, right? The square root is what gives you the crazy decimals. So with factoring, you can have a unique answer. You could just have a 5, you could just have a 7. But then when you get your crazy decimal answers, you always have a pair of something. And I'm not saying the decimals have to be the same, but I'm saying the radical that gave you the crazy decimal, that radical is going to come in pairs. Because you took like the square root of 27, and you took positive 27 and added something to it, and you took it, positive square root 27 and added something to it, and negative square root 27 and added something to it, okay? Because it came from the quadratic formula, all right? So the types of answers we get from the quadratic formula, we get irrational answers. So specifically radicals or radical answers. They come from our radicals. And then we also get our imaginary answers. That's what we saw yesterday. And our irrational and imaginary answers always have a plus and a minus. They always have a plus and a minus. They always come in pairs. Okay? 2 sets. Or a set of 2. So we're going to start off looking at a really simple example, and then we're going to see what happens after that. Okay? So the really simple example is, what if you had a nice, perfect, symmetric parabola that was centered along the y-axis, so its line of reflection is over the y-axis, and so on one side it had an x-intercept that was positive root 2, and on the other side it had an x-intercept that was negative root 2. So this is where it's got funky decimals for the x-intercepts, and those decimals are identical to each other, okay? We're going to start off exactly the same as the other side. So we're going to say, okay, x equals root 2, x equals negative root 2, and then we're still going to write the factored form, the linear factorization, even though it's going to look gross, okay? So x equals positive root 2, when we put it in that factored form, we're going to say, okay, all you do is change the sign, put it in the factored form, x minus root 2. The negative version, all you're going to do is change the sign, put it in that factored form. Okay? And then, just like before, we're still going to FOIL it out. Because if you think about how the quadratic looks before you do the quadratic formula, it looks innocuous, meaning when you look at the quadratic before you do the quadratic formula, it doesn't look scary, right? It has regular numbers, and then you do the quadratic formula and you go, whoa, that problem had weird answers, right? There's nothing about the quadratic before you plug it into the quadratic formula that tells you that it's going to be terrible in the end. You guys recall that when you do the quadratic formula? It's just that sometimes there's nice answers and sometimes there's funky answers, and ahead of time there's no clue that it's going to look terrible. It's just that, oh, when I got to the end, it happened to be a terrible looking problem, and at the beginning they all look kind of the same. Does that make sense? So even though these problems look kind of weird when we get started, by the time we get to the end of the problem, they're going to look nice. Okay? So even though this feels intimidating, just know that all the weird stuff is going to cancel out, and we're going to end up with a nice looking problem. Make sense? Okay. So we're going to FOIL this, and you guys are going to see what happens. So we're going to do x times x. X times x is x squared. And then this is where the weird stuff happens, and don't be intimidated. We're going to do x times the square root of 2, which is just positive square root 2x. And then we're going to do negative square root 2 times x, which is negative square root 2x. And then we're going to do negative square root 2 times positive square root 2. And since we're doing a negative times a positive, we're going to get a negative answer. And we're going to take a mental trip back to Math 2, because Math 2 is where we learned how to do this. So the square root of 2 times the square root of 2 is 2. Or if you wanted to show your work, you could say it's just the square root of 4. And then we all know that the square root of 4 is 2. Okay. So if you look at the middle terms, you can see that from the middle terms, you have the exact same thing written twice, but they're two opposite signs, the positive version of something gross and the negative version of something gross. So if you have positive gross and negative gross, what happens? Zero gross. The grosses neutralize each other. Does that make sense? And that's going to happen with all of these problems. Positive gross, negative gross cancel each other out always. Okay? So positive and negative gross are gone. And then we're left with just x squared minus 2. And I forgot to put my f of x's this time, so let me go ahead and put those. And that's it. And here's my standard form. And here is my linear factorizations. Okay. All right, how are your brains feeling? They okay? All right, let's make it weird again. This one has no picture. It says that we have a second degree polynomial. Can somebody tell me how many answers we should have if the polynomial is of the second degree? X squared. 2 answers. Okay, so I'm going to write x equals and x equals. I'm going to write it twice. 2 times. Okay, x equals x equals. Okay, and they tell you one of the answers is negative 3i. Negative 3i is one of the answers. Anybody know why I didn't draw a picture this time? Yeah, it's not going to cross the x-axis. So if you guys want to know what a picture of this would look like, it's probably going to look like this. And the x-intercepts are imaginary, which is why we didn't draw a picture. Probably looks something like that. I'll update after we finish finding the answer for the problem. Okay, so we've got negative 3i. Now we have to go back up to the quadratic formula. And we have to remember from yesterday when we were doing problems like this, we found the I because we were taking the square root of a negative. So the negative 3i must have come from taking like the square root of a negative 9, right? That's probably something like that. So positive 3i, or sorry, negative 3i, and then what would the other answer have been? Because they have to come in pairs. Because it would have been plus minus something. 3i, yeah, it would have been positive 3i and negative 3i, because that's what we learned yesterday when we were doing the assignment, is that they always came as plus or minus, blah, blah, blah. So positive 3i, negative 3i. Okay, so now what I'm going to do, I'm tired of writing f of x, I'm going to do y equals. Are you guys okay with that? You can write f of x if you want. Okay, So my first parenthesis is going to be what? X plus 3i. Okay, and my next parenthesis is going to be x minus 3i. Perfect. Okay, let's go ahead and FOIL it. So x times x is x squared. X times negative 3i is negative 3ix. Positive 3i times x is positive 3ix. And then positive 3i times negative 3i is going to be a negative. And then 3 times 3 is 9. I times I is I squared. And does anyone remember what an I squared is? It's something very specific. -1. Everyone remember that? Okay. I squared is a -1. So we have a -9 times a -1. What is that? +9. So we got an x squared, we got a +9, and we've got a negative gross and a positive gross. What happens with the negative gross and positive gross? They cancel. So negative gross and positive gross are gone. And then we get y equals x squared plus 9. It's 0. B is 0.
How do you get, how would you create an equation where there is a b?
You do have one, it's 0.
But, where there is a non-zero b. How do you get?
Well, you wouldn't have one for this.
Right, but, what sort of what sort of roots would you use? How would that calculate?
They would possibly, well, they'd probably be ones with real roots.
Because then it wouldn't cancel out and you'd be left with roots.
They just wouldn't be these ones. We're doing really simple examples. So they probably are ones that are more complicated. Okay, so I'm going to give you guys some of the practice problems to start with. So the homework for tonight, I'm just going to show you guys what this assignment looks like. We are not going to do this whole assignment, but I do want you guys to practice a couple so you don't lose all the information we got from these notes, okay? And then tomorrow is a very calculator-heavy day of finding characteristics for polynomial functions. So think about characteristics like domain, range, max, min, x and y intercepts, all of that stuff. And for this particular unit for polynomials, it just happens to be very calculator heavy. So the plan is we're going to do a little bit of practice with this, and then we're going to do the notes tonight. And that's what you're going to do for tonight. And then tomorrow we're going to do a little bit more practice of this and then some calculator work. That's the plan for tomorrow, okay? So let me hand this out so I can tell you which problems I want you to do, and then I'm also going to hand out the notes for tonight. Sound good? In this packet, let's decide what we want to do. So I'll show you, this is our video notes. It is, it's one page, front and back. It looks very familiar. Does it look familiar? You're like, yep, we've done that before. Okay. So if we look at this, I'm thinking maybe what we should do is go ahead and circle number 6. I want to do number 6 because I want to see how you guys feel about it. So let's do 1, 2, 3, 6. Can we do that? 1, 2, 3, 6 in the video tonight. 1, 2, 3, 6? Okay, let's do that. 1, 2, 3, 6. 1, 2, 3, 6. And so what you guys are going to work on now for the last 10 minutes of class is 1, 2, 3, 6, and then I will pass out the notes for the video tonight. Sound reasonable? Not an overwhelming amount? A comfortable amount. Marvelous. Okay.